Welcome to KINE2253, Motor Development Across the Lifespan. This lecture will discuss the 13th chapter of Lifespan Motor Development, the 7th edition, by Haywood and Getchell. This lecture will provide supplementary examples and explanations to provide a deeper understanding of the book chapter. In this lecture, students will examine the development of vision, audition, and kinesthetic systems and how these systems change with age. We will also describe how changes in these sensory systems affect our ability to move. Let's begin by first describing what is meant by sensation and perception. Sensation refers to the neural activity triggered by a stimulus that activates sensory receptors. The sensation generates a nerve impulse along the sensory nerve to the brain and spinal cord. Perception refers to the selection, processing, organizing, and integrating sensory information. Even if the sensory information is the same, an individual's perception of that information may differ. Let's look at one example of how perceptions may differ. Examine this picture. Although the sensory information on your retina is the same, the perception of what you see may differ. Do you see two faces, or do you see a goblet? Sometimes when you look at this image, you might even switch between seeing the faces or the goblet. Your sensory perception for other types of sensory information, like auditory, tactile, olfactory, and taste, may also cause similarly conflicting perceptual experiences. Let's first discuss visual development in more detail. As we saw in the previous chapters, vision plays an important role in the way we move and in the development of different motor skills. Visual acuity is defined as our ability to see objects clearly. Visual acuity is measured using the Snellen scale, where 20/20 means that you can clearly see objects that should be able to be seen clearly at 20 feet. 20/40 means that a person can see an object at 20 feet that others can normally see at 40 feet. This person's vision is half as good as a person with 20/20 vision. If you look at the figure to the right, the axial length is the length from the front to the back of the eye. This is also called the anterior or posterior poles of the eye. Differences in the axial length determines near or farsightedness. The cornea is the transparent front part of the eye that covers the iris, pupil, and anterior chamber. The cornea and lens refract light or allow light to be focused onto the retina. Differences in the cornea curvature cause astigmatism, or blurred vision, that is caused by the inability to focus the light onto the retina. Developmental differences in visual acuity have been reported during infant and child development. Kelman and Arterberry in 1998 found that infants can differentiate facial features around 20 inches from their face. This would be the equivalent on the Snellen chart of 2400. By around the age of 5 years, children's visual acuity is around 2030. Adult levels of visual acuity are reached around 10 years of age. As mentioned, this would be around 20/20 vision. There are several age-related changes in visual acuity that happens in older age. Presbyopia, which is the Greek word that means old man eyes, typically occurs around the age of 40. Presbyopia requires the use of reading glasses to see objects close by. Pupil diameter decreases to about 1/3 of that of a young adult around the age of 60. A reduction in the pupil diameter reduces the amount of light reaching the retina, such that the images appear darker even in full light. This also means that at night, older individuals have a hard time seeing objects. The lens also yellows with age. This also results in a reduction in the light to the retina. Cataracts is a clouding of the lens. Glaucoma is damage to the optic nerve. Maculopathy is damage or degeneration of a part of the retina called the macula, which is necessary for accurate and sensitive vision. All of these changes can affect the ability of an individual to perform activities of daily living and to move adaptively. In order to assist older adults and to compensate for these age-related changes, you can make sure that areas are well lit and reduce the amount of glare. In addition to visual acuity, accurate perception of space is necessary for movement. This includes the perception of three-dimensional space, or depth perception. Depth perception is the judgment of distance of an object or place in space to oneself. Depth perception may be determined from different sources. First, retinal disparity is the difference in the image on the right and left retina. Binocular vision is necessary to determine retinal disparity. The image to the right shows how retinal disparity helps determine depth. The images on the left retina are closer together than the images on the right retina. Depth is thus perceived based on this disparity between the images on the left retina and the images on the right retina. Second, motion parallax is a monocular depth cue caused by our own head motion. Objects that are close to us appear to move faster than objects that are further away. Lastly, optic flow is a change in the optic array as you move forwards and backwards. Developmental changes in visual perception of space and depth have been examined. For example, Nanas and Jonas in 1994 found that 1-month-old infants blink more when shown images that appear to be approaching the eye. This blinking is a protective mechanism that prevents objects from hitting the eye. This suggests that infants can differentiate movement from a change in size. This is because objects that approach the eye appear larger than objects that move away from the eye, which look smaller. Walk and Gibson in 1961 also examined depth perception in 6 to 14-month-old infants. Similar to the image on the right, infants were placed or moved towards the edge of what appeared to be a sudden drop-off. There was no actual drop-off since the surface was covered in plexiglass. But nonetheless, as the infants reached the edge, they became fearful, suggesting that they could perceive the potential danger caused by an apparent drop-off. Developmental changes in neurological development necessary for visual perception was examined by Held in 1985 and 1988. This researcher found that by 6 months of age, ocular dominance columns had begun to develop. Ocular dominance columns form when information from one eye is mapped to one column, while information to the other eye is mapped to an adjacent column. Retinal disparity depends on knowing which eye is sending the information, and thus you can compare the information from each eye. The thresholds for depth perception remain stable across development. However, older adults tend to fail depth perception tests more frequently compared to young adults, and it is unclear why this is the case. Edge detection is also important for object perception. Edge detection is the ability to determine the boundary between objects from the background environment. The image to the right is an example of edge detection because you use the color information to determine the boundary between the face or the goblet. Similarly, figure and ground perception is the ability to see an object as distinct from the background. Sometimes the differences between the object and the background are more or less obvious depending on the stimulus. This is an example of figure-ground perception. In this picture, there are several objects that can be found, including a pitcher, a key, and a hammer. Another aspect of object perception is what is called whole and part perception. This is the ability to discriminate parts of a picture or object from the whole, while integrating those parts into those wholes and perceiving them all simultaneously. The image to the right of the panda is an example of whole and part perception. Although the contour in the panda's back and head are not continuous, we can tell that the different parts of the image go together to create a panda. Developmental changes in object perception have been reported in young children. For example, Williams in 1983 and Temple et al. In 1979 both reported age-related differences in figure and ground tasks between 4 and 6-year-olds and 6 to 8-year-olds. An example of this would be the image of the pitcher, key, and hammer. KINE in 1975 found that children under age 9 have difficulty integrating parts and the whole in a picture. An example of this is the image to the right. The pumpkin's face is created by the individual fruits. The eyes are the orange slices, the nose is the strawberry, and the mouth is the banana. Together they create a face. Developmental changes in object perception have also been reported with respect to size constancy. Size constancy is the perception of the actual object size despite the size of the retinal image. The image on the bottom compares the size of the objects in reality and what the images of these two objects are in the retina due to their relative position towards or away from the eye. Despite one object being close to the eye, and as such results in a smaller retinal image, one can perceive the objects accurately as being the same size. Slater et al. In 1990 found that regardless of the distance of an object from the eye, infants will perceive the size of an object accurately. This suggests the ability to perceive size constancy is developed very early. Similarly, the developmental changes in shape constancy also appear very early. Shape constancy is the perception of the actual object's shape despite its orientation to the viewer. For example, one can tell that the 3 images at the bottom are all of a door, despite the different orientations of those doors. Infants can perceive these types of shape differences. Developmental changes in the perception of spatial orientation of objects appears to develop a bit later compared with size and shape constancy. Spatial orientation is the orientation or position of objects as they are located in space or within an image. Gibson in 1966 and Pick in 1979 both reported that children at 3 and 4 years can learn directional extremes like high and low, over, under, front, back, but they have a difficulty with intermediate orientations. Williams in 1973 and Nuss and Shulman in 1976 found that by age 8, children can differentiate various oblique and diagonal orientations in addition to the extreme orientations described above. Given that many of the studies we have discussed have reported the ability of infants to discriminate shape or size or motion of objects, you might ask yourself, how exactly do you measure infant visual perception? Habituation is the adaptation to a stimulus. It is essentially the equivalent of getting bored when you see the same stimulus many times. Infants show what is called preferential looking. Infants look more at novel, surprising, or different objects. In contrast, infants' attention wanders when they habituate to a stimulus or object. So how exactly do you determine infant habituation or preferential looking? First, you will show an infant a stimulus and measure the amount of time the infant looks at that stimulus over time or over repeated exposures. Second, you will change the size, shape, or orientation of that object and present that new stimulus side by side. Third, you see if the infant looks at the new stimulus as if it's different.
To give you a better idea of what infants or children experience during a visual perception task, here is an example of a habituation task. You will be shown 2 pictures on either side of a fixation cross. The pictures will be shown for 2 seconds each. Sometimes the 2 pictures are the same, and sometimes the 2 pictures are different. Pay attention to which picture you tend to look at more, the left image or the right image. Let's begin. Okay, so what did you notice? Did your eyes move to the picture that was different? Which of the 2 different pictures were more interesting to you? The one that was upside down or the one with more fur? Imagine being shown the same pictures for many, many more times. It's obvious why infants habituate or grow tired of the same pictures shown over and over again, and why their eyes tend to move to new or novel pictures.
In addition to object perception, motion perception is critical for movement. Recall that it is easier to kick or strike a stationary ball than to kick or strike a moving object. Specific regions of the brain within the cerebral cortex perceive visual motion. One area, called area MT for middle temporal, processes visual motion. To determine visual perception of motion, you must determine the detection threshold. This is the point along a continuum at which the energy level is sufficient for one to register the presence and movement of a stimulus. Developmental changes in motion perception were reported by Wadham-Bell in 1996. This researcher found that the direction of motion was not well perceived until about 8 weeks of age. Aslan and Shea in 1990 found that a stimulus must move fast in order for an infant to detect the motion. By around 6 weeks, only very slow velocities are difficult to perceive. Elliott et al. In 1989 found that older adults have difficulty perceiving motion at or near the detection threshold. This suggests that movement needs to be fast or more obvious for older adults to detect the motion. Okay, before we move on to kinesthetic development, let's sum up what we have learned so far about the development of visual sensation and perception. First, differences in the structure of the eye can affect visual ability, particularly visual acuity. Visual acuity develops across infancy and early child development and reaches adult levels around age 10. Aging-related changes in visual acuity may be due to degeneration or damage of different aspects of the eye. Second, the perception of objects includes the location of those objects using depth perception, edge detection, figure ground perception, whole and part detection, and the perception of the size, shape, and orientation of that object. Some of these perceptual abilities are developed during infancy, while some continue to develop or change across childhood. Studies use habituation or preferential looking to determine infants' abilities to perceive different aspects of visual objects. Lastly, in addition to static object information, motion perception also develops during infancy and is necessary for object interception and object manipulation.